Welcome everyone. In this video lecture, we will write the state space representation for the RC circuit. So, as we know, all linear physical system or all physical system can be written in terms of state space representation. So, what I am saying, all physical system can be written in terms of state space representation. Okay, so basically the space representation we have to write any physical system like x dot is ax plus du and y is equals to cx plus du. These are the two equation we can say, where the first one is called the state equation. The first one we can say the state equation, and second one is our output equation. Okay, so any equation can be written in this form. So this one is our very fundamental RC circuit. Okay, so first of all, in such situation we have to identify the state variable. Okay, so if in a circuit, if some capacitor is there, okay, some capacitor is there, the state variable, I'm not going for the all theory, a state variable will be Vc. And if some inductor inductor is there, so in that situation you have to take IL as a state variable. Okay, in that case you have to take the IL as a state variable. Okay, so these are the two things you have to remember. Okay, for capacitor and order order. Okay, means what is the order? So in this one, suppose one capacitive term is there, energy storage element is one, so order of the state equation is first order. Okay, so order depends on the storage element present in the circuit. In the circuit. Okay, so these two three points we have to know. In addition to that, some more uh, basics I want to say. X dot equals to ax plus bu. Okay, so here what is x? X is the state variable. Okay, so okay, this question is very easy, but we have to know the some what is x? State variable. Okay, x is the state variable. A, the term A is our state matrix. State matrix. Okay, and that state matrix of the system. State matrix of the of the system that holds the property of the system. It will clear, means if we solve this problem now, then it will very clear now. Now B is the input matrix. Input matrix. Okay, and this B is the input matrix in which this B is that some say the variable or parameter related to the scaling of the input. We can say the parameter related to the Scaling of input. Okay, input API I'm writing. Okay, A is there, B is there, C is the output matrix. Output, I'm writing output matrix. Okay, output of a system, output matrix you can say, and U is the input variable. Input variable. So these are some points. Okay, so now in this situation or in this circuit, we have to write the static space representation. So first of all, what we have to do, first try to write the variable. Means this one is order one, order first order. Okay, order one because only one capacitor is there, and the state variable. The state variable we can say VC, voltage across the capacitor. So this one I am saying this one is our VC. Okay, this one is our state variable. Clear? And the input, U represent the input. Here I have written U is the input. Okay, U is the only input you can say. So U is our simply Vs. Okay, so these are 3 points. Okay, so now how to write the equation? Okay, so first of all, for example, I am saying there is some current flowing, that is our IR. Some current is flowing IR. Okay, say the current is IR, and this current I am saying say IC. Some current is flowing, and this current will be say IR naught. Okay, so if we apply this point is say A. So if we apply KCL at point A, okay, if you have to write a state space representation, you have to first write the variable. Okay, means what should be our state variable. So here capacitor term is there, so only one state variable VC. Okay, that uniquely define the system. Okay, so now what we can write KCL. So total incoming current at this point IR equals to IC plus IR naught. Okay, now IR can be written as Vs, this voltage minus Vc by R equals to IC. The current IC equals to C dVc by dt plus IR naught. IR naught we can write as Vc by R naught. We can also write V naught by R naught, but here I am writing Vc by R naught. You can write. So I am writing. Is it clear? Vc by R naught. This voltage because Vc equals to V naught. Okay, this voltage and this voltage Vc equals to V naught. So we are writing like this. Okay. So now what we can write C dVc by dt. Okay. In the suppose we are putting in the left hand side. Okay. Then what we can write if we put this one is a okay in this side only. So what we can write minus Vc. Okay, and if we solve, if we put this one in this side, 1 by a simple simplification, 1 by R plus 1 by R naught plus Vs by R, Vs by R. Okay, so once again what we can write dVc by dt equals to minus Vc, and if we divide with all term with R C, sorry, so RC plus simple calculation. Okay, so now what we observe that this dVc by dt is our what? For example, this one is our state equation because we have to write in terms of x x dot state variable differentiation. So it should be our x dot. Okay, So this one is our x dot. Okay. Then this is x and ax. So other term is ax plus bu, or simply write, we are writing like this. So you can also write ax. So this one is our state equation. Okay. So here what we can say, x is this vc. Okay. So what is the value of x? X is our simply vc. Clear? a parameter. A parameter is minus, we can write as 1 by rc plus 1 by r naught c. Okay. A state matrix of the system that holds the property of the system, and it is multiplied with the state variable. So this was the a. Okay. Then after, what is the value of b? B is our 1 by rc, and u. U is nothing but simply our vs. So we have written in terms of this. Okay. Like x is our vc. Okay. A is our this. Clear? This is a very easy example. B is this, and u is this. Okay. So this one is a state equation. Okay. So it is very easy. Okay. Then after, we have to write it for the output expression. So this one is a state equation. Okay. Clear? So now if we have to write the output expression, so V naught is nothing but simply Vc. So what we can say, the output y equals to, we have to write y as a function of cx plus du. So here y is our V naught. So y is our V naught. Okay. So what we can write, V naught c into x. So c we can say 0. X is what? Vc, state variable. So 0 into Vc plus d. What is d? D is what? Only Vc is there. V naught equals to Vc. Okay, wait. V naught equals to Vc. So first c into x. Okay. And then this value is 0 into Vc. Okay. 0 into Vc plus du. Oh, sorry. It should be 1. Okay. Sorry. Uh, Means V naught equals to just same as that of Vc. Okay. So C value is 1, and this should be Vx. Plus D is will be 0, and U is our input variable. U is our Vs. So this one. So this one is nothing but simply V naught equals to Vc. So here the C value is 1, here C value is 1, and D value is 0. So this one is V naught equals to Vc, and this one is the status output expression. Okay. So in the next video, I will try to go for the RLC circuit. Okay, a state space representation. Okay. So once again, this one is our circuit. So the final output, you can write it. If this one is the R naught, R C, and this one is our what? Vs. Okay. So the equation is like dVc by dt equals to minus Vc 1 by Rc plus 1 by R naught C plus Vs by Rc. Okay. And V naught equals to the output function, V naught equals to Okay, so this is the status space representation of a simple RC circuit. So it is very simple, but you have to know some fact. For capacitor, we have to take the variable VC only. Okay, for inductor, put IL. And think about, so in the other video, we will think about the second order status space representation, second order equation we will write for the RLC circuit. So thank you for watching this video. Thank you.